immediately when I start it, of course the bell rings. Alright, 2008, consider the logistics differential equation, fluidity. Let y equal f of t be a particular solution to the differential equation with f of 0 equals 8. Fantastic. A slope field for this differential equation is given below. Oh, look at the carrying capacities. Looks like it's 1, 2, 3, 4, 5, 6. Looks like it's 6, right? Is that the, yeah. So the carrying capacity is 6. Of course, that's what it says there. A slope field for this is given below. Sketch possible solution curves through the point 3, 2, 1, 2, 3, 2, and 0, 8. Oh, that's easy. That's super easy. All I'm doing is like following the contours. So like if I started here, right there, and then go up and then like whoo, something like that, and then come down and something like that. Easy. And then if I was up here, I could go like whee, like that. So that's like ridiculously easy. You're just following the contours of the slope field, and there you go. Those are the possible curves. What if that was 2 points each? Or I mean, like 1 point each, so 2 points. What if they are? It was just that one's worth 2 points, and you get it done in an instant. Ooh, that was a good snap. Use Euler's method, starting at t equals 0 with 2 steps of equal size to approximate f of 1. Oh, okay. Where do I start? Well, it says to start with 0, t equals 0. So I'm going to make a chart. So I have my x, my y, and my dy dx. So here we go. And I'm starting at 0, and I want to approximate f of 1 with 2 steps. So I take one step, must be to 0.5, right? And then I take another step, it must be to 1. So those are 2 steps, and the step size is 0.5. That's just me thinking about it. Great. So the next thing that I do is 0. I know when I plug in 0, I get 8 for y, so I got that. And then I have my dy dx, or in this case, t. So let's find dy dt. There, t values. That would be 8 divided by 8 is 1. Times 6 minus 8, that's negative 2. So my slope here is negative 2 over 1, but I want my step size to be 0.5, so I can just multiply by 0.5. Easy enough. This is no calculator, right? No calculator on this one. No calculator. So, let's mind times by 0.5. That's the same thing as negative 1 over 0.5. Okay, so this changes to 7 because I step for the x, and then I also step for the y, negative 1. So I go from here down 1. Okay, easy enough. All right, and then now I get dy dt again. Now I'm using 7. So in this case, it would be 7 over 8 times 6 minus 7, and that's just negative 7 over 8, right? Because this is just negative 1. Okie dokie. Negative 7 over 8. And now I'm thinking, okay, how do I make this a 0.5? 0.5 divided by 8, right? Because then that would cancel out. So I'm doing 0.5 divided by 8. And so what do I get? That's crazy. I think I might change it to a fraction because this is kind of disgusting. So that's like 1/2 over 8, right? Which is the same thing as 1 over 16. So 7 over 16? No? Maybe. Hold on. Yeah, that seems to be it. And then what do I do? Oh, come on. I have to have this times negative 7 there. So this is, I'm going to say negative 7 over 16 over 0.5. So that's, I'm going from here to here, and it looks like I'm going 7 minus 7 over 16. So I got to put this over 16. No, sorry, over 1 times 16. I'm getting a common denominator here. Now it's just regular arithmetic. So what is that? 16 times 7 is something that I'm going to just write down. 42 7 times 1 is 7, 8, 9, 10, 11, 1, 1, 2. Okay, so 1/12 over 16 minus 7 over 16, right? Because I'm going from this, and I'm adding that much, which is a negative, so 12, 11, 10, 9, 8, 7, 6, 5. 105 over 16. So there we go. 105 over 16. So f of 1 is approximately 105 over 16. So that's part B. Easy enough. I mean, a little bit of complicated numbers, but nothing too scary. Write the second degree Taylor polynomial for f about t equals 0 and use it to approximate f of 1. So we should get something close to this. But it said write the second degree Taylor polynomial for f. Well, we could do that pretty easily because we have the Taylor series formula, right? Let's try that. And is it centered about 0? Centered about t equals 0. Yes. Okay, great. So we're going to be plugging in 0 to the derivative, and in factorial x minus 0 to the n. So we're using that formula. So the first derivative, actually the 0th derivative, what is that? We are given that. That's regular f of 0, and that's 8 is given right there. And then f prime of 0, well, that's the same thing as dy dt, no? No? Is it not? And I'm plugging in a t value of 0, so t equals 0. So what? We have to know what y is. Luckily we do. Look, this is the crazy part. If t is 0, that means for my function y, I'm plugging in 0 to f, but they give us that. That's 8. So that's maybe a little bit of a tricky part, but we have 8 over 8 times 6 minus 8. So that we got already, and that's 1 and negative 2. And now I need my second derivative, dy squared over dt. No, d squared. There. So I need this part. And I can do that by taking the derivative here. So that's what I'm going to do. And I'm using the product rule and probably chain rule or implicit differentiation because I'm taking the derivative with respect to t and I'm taking it of y. So first, y over 8 d second, that's negative dy dt. First d second plus second d first, and that's 1/8 dy dt. And I already know what dy dt is. I'm plugging in 0. So what was dy dt? That was this, of 0. So we got negative 2. That way I don't have to plug in way too much. And if I'm plugging in t equals 0 to y, I get 8. So hopefully you understand what I'm doing. Instead of like substituting this in for that stuff and then plugging in t equals 0, I already know that this is going to equal negative 2 when t equals 0 because I've just found that. So this part is going to be negative 2, and this part is going to be 8. And this is going to be 8. So I got 1 times positive 2 plus negative 2, right, for that part, times negative 2 over 8. Okay, so that's just plus 4 over 8. That's just 1/2. 2. And what is this? Over 1 times 2 times 2. That's 5 over 2. I don't know why I did 2 equal signs. 5 over 2. So what the heck am I doing that for? Well, I needed those. And now I could just put in the rest. It needs a second degree Taylor polynomial, right? The second degree Taylor polynomial, all we're doing is using this formula. So the first part, is it f? Are we doing that? To approximate, and use it. Oh, and use it to approximate f of 1. Okay, so f of x is going to be equal to the 0th one, so the 0th derivative at 0, that's 8. X to the 0, that's just 1 over n factorial, 0 factorial, that's just 1. So 8, and then plus a negative 2. Okay, so maybe minus. Minus 2 times, so that's this part, x to the, so this is n is 0, n is 1. So 2x over just 1 again, because n factorial is just 1 factorial. And then second degree polynomial. So I need to keep going. That's why I got the other derivative there. And I have 5 over 2. That's this part. And then x to the second power, because n is 2. So x squared. And n factorial, 2 squared, or 2 factorial is just 2. So I'll put that there. So I get 8 minus 2x plus 5x squared over 4. However, it is t. It says to approximate f of t, so I should have written 8 minus 2t plus 5t squared over 4. I don't think you'd get points marked off if you had x in there instead. So that's the second degree Taylor polynomial, and it said use it to approximate f of 1. So the approximation would be 8 minus 2 plus 5 over 4. What is that? I would leave it like that, actually, and be done with it. But that comes out to be 29 over 4. Sweet. Okay, that's great. And then what is the range of f for t greater than or equal to 0? What is the range for f? What does that mean? So this one's kind of tricky. You might think, so it says, what is the range for t greater than or equal to 0? And then my first thought was, wait a minute, it could be this or it could be this. But that was only for part A. It actually says in the question, I had to go back and look, consider the logistic differential equation there. Let our function y be the particular solution to the differential equation with f of 0 equal to 8. So that's starting here. So really we're just looking at the range for this. So for something like that. And it should be really, really easy. So for part D, we are only talking about the top part because of what they give us. And it says, so if you get confused, definitely reread the problem. But it says for t greater than or equal to 0. So that means from here onwards, which gets rid of that part. So the highest value that we could have is 8, because that's what it is at the very beginning, and then we decrease from there. So I can say the range is like all the y's inside the interval from, well, what's the lowest value? There's an asymptote at 6, so I would say 6 not including, and all the way up to 8, including 8. And that's it. So the weirdest part about that one is realizing they're only talking about the top part because of the actual initial conditions that they do give us. So if you get confused, reread the problem. I'm done with this. Good day.